we are going to explain what is the quantum efficiency of the photoemissive cell. Now this is the cathode of the photoemissive cell or the photoelectric cell that receives a certain radiation formed of a certain number nr of photons. nr represents the number of photons that are received by the cathode. Not all of the received photons are able to extract electrons from the cathode. And as a result, the number of emitted electrons would be less than the number of received photons. nr will represent the number of photons received by the cathode, and Ne will be the number of electrons emitted by the cathode. The number of received photons is always greater than the number of emitted electrons, since not all the photons are capable of extracting electrons. The photon that is able to extract an electron is called an effective photon. The number of photons that are able to extract electrons is called the number of effective photons, which is equal to the number of emitted electrons. The number of effective photons is always equal to the number of emitted electrons. Now, what is the definition of the quantum efficiency? Let's denote the quantum efficiency by R. It's equal to the number of effective photons over the number of received photons, which is equal to the number of emitted electrons over the number of received photons by the cathode. This is the quantum efficiency of a photoemissive cell. This is an animation showing the mechanism of the extraction of the electrons by the photons. We see that not all the photons extract electrons. The number of photons received by the cathode is always greater than the number of emitted electrons by the cathode. Now we're going to solve an application. Consider a monochromatic light source of wavelength 0.55 micrometers and having a power of 18 watts. The source emits light uniformly and in all directions. 1 meters away from the source, we place a cathode of the photoelectric cell of surface area 3.2 centimeters squared. Given Planck's constant 6.6 times 10 to the negative 34 joule seconds and the speed of light in vacuum 3 times 10 exponent 8 meters per second. First question, calculate the value of the quantum of energy of the source. What is the quantum of energy? Quantum of energy is equal to h nu. H nu is equal to hc over lambda. Replacing the values, we get 6.6 times 10 exponent minus 34 times 3 times 10 exponent 8 and divided by the wavelength, which is 0.55 times 10 exponent minus 6 to convert to meters. And the quantum of energy of this source is equal to 3.6 times 10 exponent minus 19 joules, which is also the energy of one photon of the source. In part 2, deduce the number of photons emitted by the source in each second. We know that the formula that gives the power of the source is equal to nh nu, where h nu is the quantum of energy. Then this is equal to n times E. So n equals to P over E, n equals to 18 over 3.6 times 10 exponent minus 19, and the answer is 5 times 10 exponent 19 photons. This is the number of photons emitted by the source each second. Part 3. At 1 meters away from the source, we place the cathode of the photoemissive cell that has a surface area of 3.2 centimeters squared. Calculate the luminous power received by the cathode. The power of the source distributes in a spherical way. That is to say, the power spreads over concentric spheres of center S. So when the light reaches the cathode, the luminous power will be distributed over all of this big sphere. Let S be the surface area of this big sphere. The radius of this big sphere is 1 meters. Hence, its surface area is 4 pi r squared. The power that distributes over this surface area is 18 watts. Since the luminous power distribution over the surface of the sphere is uniform, then the power and the surface area have to be proportional. If P is the power distributed over the surface area S, then the power received by the small surface area is PR. The power of the source is distributed over all the big surface. A part of this distributed power is received by the small area. Part of this big power is received by this small area. So PR, which is denoted as P received, is equal to P over S multiplied by the small area. This is 18 over 4 pi. The radius is 1. So 1 squared multiplied by 3.2 times 10 exponent minus 4 in order to convert from centimeter squared to meter squared. And the answer is 4.6 times 10 exponent minus 4 watt. This is the power received by the cathode. In part B, deduce the number of photons received by the cathode in each second. PR is equal to the number of received photons, which is nr, multiplied by the energy of a photon, which is h nu. This is equal to the number of received photons multiplied by E. So the number of received photons each second is equal to PR over the energy of a photon. NR is equal to 4.6 times 10 exponent minus 4 over 3.6 times 10 exponent minus 19. The answer is 1.3 times 10 exponent 15. This is the number of photons received by the cathode each second. Note that the source emits each second and in all directions 5 times 10 exponent 19 photons. Only 1.3 times 10 exponent 15 photons reach the cathode. The numbers are of the order of 10,000. So 1 out of 10,000 photons emitted by the source will reach the cathode. In part C, knowing that the quantum efficiency of the cell is 10 exponent minus 3, calculate the number of electrons emitted by the cell each second. Note that not all of the received photons are effective. only 10 exponent minus 3 of them are effective. That is to say, 1 out of 1000 received photons is capable of extracting electrons. 1 out of 1000 received photons will be capable of extracting an electron. Calculate the number of electrons emitted by the cell each second. From the definition, the quantum efficiency R is equal to the number of effective photons or the number of emitted electrons over the number of received photons. Now we have the efficiency and the number of received photons. Then the number of emitted electrons is R times number of received photons. This is equal to 10 exponent minus 3 multiplied by 1.3 times 10 exponent 15. The result is 1.3 times 10 exponent 12 electrons each second.